Bismillahirrahmanirrahim. This is our first lecture on semiconductor devices, course code 212. And in this lecture, we will start with chapter number 1. The title of chapter number 1 is Semiconductor Diodes. And the textbook is Electronic Devices by Boylston and National Sky. So our first article is article number 1.2. Right. So let us start with the definition of semiconductors. Semiconductors are a special class of elements having a conductivity or electronic conductivity between that of a good conductor and that of an insulator. In the definition, we can see the word conductivity. Now, sometimes the word conductivity is confusing, whether it is electronic conductivity, whether it is thermal conductivity, or audio conductivity. In the case of semiconductors, the conductivity that we are referring to means electronic or electrical conductivity. The semiconductors have electronic conductivity in between of a good conductor and those of an insulator. Conductors are elements that those have the free electrons very close to the valence shell. The energy gap between the free electrons and the valence shell is very small, and in some cases it is overlapping. A good conductor requires very minute amount of energy to be absorbed by an electron in the valence shell to move into the conduction shell. Conduction shell is where the electrons they will move, and hence we will get an electronic current. On the other hand, the insulator, if we look into the microscopic level of an insulator, the activities going inside the Bohr atomic model is that there is a large energy gap between the valence shell and the conduction shell. Therefore, the insulator requires much large energy to be provided to the electron in the valence shell. So this very large amount of energy will be absorbed, and hence the electron will jump into the conduction shell. So this property makes the insulator not to conduct current easily. And in semiconductor case, semiconductors, their position lies in between. They are not perfect conductors and neither are they perfect insulators. We make good conditions for them in order to allow current to flow. And when we disengage from these conditions, these materials they stop conducting current. Semiconductor materials they can be divided into two types of classes. First is the crystal type or the single crystal where we have a uniform element of one material, or second class is that we have a compound. Compound meaning that is a composition of many elements, at least two. Single crystal conductors such as germanium and silicon have a repetitive crystal structure. Here, the word repetitive crystal structure means or refers to intrinsic materials. Those materials which are uniform, they are pure from any other elements besides the elements that we are interested in. They have a uniform crystal. And the compound semiconductors, they are a mixture, a composition of at least two elements. For example, gallium arsenide. Second example, cadmium sulfide. Third example, gallium nitride. And fourth example is gallium arsenide phosphide. So we can see three examples of two elements forming compound semiconductors, and we can see three examples where we have two elements forming compound semiconductors, that is gallium arsenide, cadmium sulfide, gallium nitride. These are the three examples where we need two elements to form compound semiconductors. Whereas we also see one example of three element compound semiconductor, that is the gallium arsenide phosphide. Now both of
Okay.
them, that is the single crystal semiconductors and compound semiconductors, they are conducting electrons not as poor as insulators, but also not as good as perfect conductors. So we have to make conditions, we have to make the right conditions to these semiconductors in order to allow them to flow current.
सर देयर इज अ क्वेश्चन सर। सर कौन से सेमीकंडक्टर बेटर हैं, सिंगल सेमीकंडक्टर या कंपाउंड सेमीकंडक्टर्स?
The question is that out of these two classes, single crystal or compound, which one is better? Both are fine depending on your application. What are the applications? One application of electronics means single components. For example, single diode, single transistor, single MOSFET, single FET. Other examples include VLSI circuits. For example, the computer chips that you are using, they are all composed of semiconductor materials. But these two are two different examples. We will see that gallium arsenide is much better in terms of VLSI, whereas single crystal are much better, they give much better performance while using as a discrete component. Now, what is a discrete component, by the way? So it is one unique component. It is not a mixture of many components. For example, discrete component like single diode, discrete component like single BJT transistor. In such cases, silicon or germanium crystal structures give much better performance. I am saying they give much better performance, meaning that it is not impossible to make single crystal, it is not impossible to make diode out of gallium arsenide. No, it is possible, but the performance will far exceed compound semiconductors. But on the other hand, if we look at into the processor, microprocessor chips, for example, those produced by Intel, those VLSI circuits, in those cases, the compound semiconductors, they give much far better performance. So the answer is it depends on your application.
Sir, which one is the less power absorbing?
Most power efficient is gallium arsenide. In terms of power, gallium arsenide. But gallium arsenide, they are much difficult to manufacture as compared to single crystal semiconductors. We need much more intrinsic processing procedures to unify or to make out the compound semiconductor. So as a result, the burden will be borne on the price of the manufacturing process. And in this slide, the last sentence, I'm following the last sentence that the three semiconductors used most frequently in the construction of electronic devices are germanium, second is silicon, and third is gallium arsenide. These are the most popular or frequently used semiconductors for electronic devices. Now we come to the next slide. The next slide will present a very brief history of semiconductor materials. In this slide, we will go through a very brief, a very quick history of the semiconductor materials. During the start of the electronics, germanium was used most exclusively because it was relatively easy to find and was available in fairly large quantities. The germanium based diode was invented in 1939 and the germanium based transistor was invented in 1947. But the diodes and transistors constructed using germanium as a base material suffered from low level of reliability due to sensitive changes in temperature. Now, if we look at this sentence, that diodes and transistors constructed using germanium as base material. What is the meaning of this word base material? The base material refers to that a single or a simple crystal of germanium is of no use. We have to make conditions, correct conditions to develop diodes. We have to make correct conditions to develop transistors and other electronic components. Base material will be your intrinsic material. It is the material which is pure from any impurity. If we take the example of single crystal of germanium, then if we look in using a microscope, we will find the base material equal to a perfect crystal of germanium, which almost has 98% pure germanium. But it is of no use. We have to insert some required impurities so that we can develop p-type material and n-type material. And in addition, just developing p-type material and n-type material is not enough. We have to also develop the correct concentration. As we will see later in this chapter, we have to develop the correct concentration of required p-type material and n-type material. And this concentration, we will see, that leads to the possibility of small currents controlling much larger amount of current, the term beta or the term gain current. Gain represents the amount of concentration that the manufacturer had put into a given model of transistor. And if we talk in terms of the diode, then the concentration of the diode will represent, or it will refer to, the amount of current handling capacity of the diode itself. This was the slight introduction to the word base material. Base material is of no use. We have to insert impurities, which is called doping, to make n-type material and p-type material. Only then we can develop transistors, only then we can develop diodes, and so on. Now, another important word in the same sentence is sensitivity to changes in temperature. I would like all of my students to remember that electronics is very sensitive to temperatures. What do we mean by electronics very sensitive to temperature? Is that the properties of the electronic component will change with the change in temperature. It is for this reason that we use heat sinks that extract heat energy from our electronic component and disperse the heat energy into the atmosphere, only for one purpose, so that the temperature of the device remains cooler and remains uniform. Now, this was a problem with germanium, that the germanium crystal was too much sensitive to temperature. This led to the invention of silicon electronics. Now we come to the fourth slide. In 1954, the first silicon transistor was introduced, and silicon quickly became the semiconductor material of choice. Not only is silicon less temperature sensitive, but it is one of the most abundant material on earth, removing any concerns about availability. These were the two major advantages of using silicon as our base material. First major advantage was that silicon is less temperature sensitive. The word is less temperature sensitive. So the silicon gives better performance at higher temperatures. Therefore, it means that we need a smaller heat sink. A smaller heat sink means that we can now reduce the volume of entire electronic component. So a simple change in material gave us much better performances in terms of space, in terms of speed also. And then silicon is available in abundant quantity. Now we come to the gallium arsenide. Gallium arsenide was was more difficult to manufacture at high levels of purity. This was the problem in the start with gallium arsenide, that it is that it was difficult to manufacture at high levels of purity. It was more expensive also, and it had little design support in the earlier years. We have now three words to discuss in this sentence. First word is high level of purity. High level of purity means that the base material is free from unwanted elements, so that there is less number of unwanted elements. These unwanted elements will change the chemistry of the compound. They will introduce unwanted phenomena. They will introduce large resistances, plus they will introduce the requirement of increasing the volume or the size. So these electronic devices, for example your mobile phones, for example your laptops, your computers, they are small because of the reason that the material being used is very much pure. It has high level of purity. If it was unpure, then the size would have been much larger. If you can look back in the early 80s, the early 90s, those machines, those, even though they had good impurity at that time also, but since our machines nowadays they are much smaller due to that we have improved the purity levels, and at those times they were much more expensive. This was the second word. And the third word is little design support. Little design support here means that at those time when gallium arsenide was introduced, there were very small number of components using gallium arsenide. Hence, the manufacturers, they were disencouraged. They were not interested to manufacture gallium arsenide components because there were little components being used. However, the scientists, the engineers, they knew that the gallium arsenide will give much better performance if the problems could be overcome. Therefore, in the third paragraph, however, as the demand of increased speed resulted in more gallium arsenide research, to the point that today it is often used as base material for new high speed, very large scale integrated circuit design. So now it has become the industry standard to use gallium arsenide where very large speed is required. Very large speed means circuits which are very small but they give us ultimate performance. And if we can look at the last line, the very large scale integrated circuit, ये VLSI means the internal circuitry of your regular integrated circuits, जिनको आप normally microprocessors में, microcontrollers में, the mobile phone, all electronic components, you can find them here. So they are very, very, very small scale circuits, and these circuits, they have diodes inside, they have transistors inside, they have even resistances made up from electronic components, all integrated into the chips, and they are normally in the industry, they are called chips with a certain number of connections. So VLSI. Okay, so now we will come to slide number 5. Slide number 5 brings us to our new article. This article is article number 1.3. The title of the article is Covalent Bonding and Intrinsic Material. I am pretty much sure that all of my students, they have a clear-cut idea of covalent bonding during their FSCs or even metric classes. However, in this stage, we will have a very brief look over these compound materials since we need them, or we need to understand the physics to develop p-type material and n-type material. So article number 1.3, covalent bonding and intrinsic material. Covalent bonding is a nature of how two elements or how two atoms of two different elements, they interact with each other. Each atom of the element requires the fulfillment of the last octave, and how one atom fulfills this requirement will define the bonding. So we have ionic bonding, where one atom completely absorbs the electron of another atom and becomes ionized, but it completes its octave. The second technique is to use covalent bonding, where two different element atoms, they share with each other the electrons of each other, so that both atoms of different materials, they complete their outer octave. Okay, Jita, I will now read from the slide. The fundamental component of an atom are the electron, proton, and neutron. And this is your normal Bohr's atomic model structure that we will discuss. In the latest structure, neutrons and protons form the nucleus, and electrons appear in fixed orbits around the nucleus. The Bohr's model for three material is provided in figure number 1.3, and here we have figure number 1.3. Three diagrams A, B, and C. Figure number 1.3, part number A, shows the atom for a silicon element. Figure B shows atom of germanium element, and figure C shows the compound structure, atomic level compound structure of gallium arsenide. Now, if we look at part number A, silicon, we see the normal Bohr's system of the atom. The Bohr system of the atom means that the neutron and proton, they are in the center. The neutron, they have zero polarity. They are neither positive nor negative. And inside the nucleus, we will also find protons. Protons, they have positive charge. Now, electrons, they circle around the nucleus. And in the case of silicon, we have 14 electrons. These electrons, they are distributed in shells, and the outermost shell is called the valence shell. And for silicon case, especially for silicon case, we will find 4 valence electron. 4 valence electron means that there are 4 electrons in the valence shell. Now if we look at germanium, part number B, if we look at figure part number B, in the case of germanium atom, we will find that again the Bohr system remains the same. Inside there is the nucleus, and outside there are circulating electrons. And in germanium case also, we find that the outermost valence shell is again 4 electrons in the valence shell. Now, let us stop over here. Is this germanium or silicon complete in terms of octaves? Is the silicon atom complete, or is the germanium atom complete? So in terms of charge, it is complete. That is, the number of protons is equal to number of electrons. But the outermost shell is incomplete in terms of the number of electrons. How many electrons, by the way, do we need in the valence shell? 8 or
Four more.
16?
Sir, 8 electrons for a complete valence shell.
What will happen if we get 16 or 32 electrons in the valence shell?
Sir, this will be highly excited states and radiation will be emitted.
To complete the valence shell, we have to maintain 8 electrons in the valence shell. But when the silicon atom acquires 8 electrons, the charge condition on the atom will be unbalanced. That is, there will be much more electrons as compared to the protons. Hence, the silicon atom will have a net negative charge, but with the complete octave. Same explanation can be applied to the germanium case. In germanium, we also see 4 electrons in the valence shell, and there is a tendency, or there is a opportunity for adding 4 more electrons in the valence shell. But again, in germanium also, when we add 4 more electrons, the germanium atom will not be neutral. It will have a net negative charge. And then if you look at figure 1.3, part number C, we see the gallium and arsenic compound. The gallium having 3 valence shells and arsenic having 5 valence shells. So how do they make a molecule anyway? How do they make a molecule? It's quite simple. That is, they form a covalent bond. The gallium and the arsenic elements, they form a covalent bond where the 3 valence shell of the gallium element and the 5 valence shell of the arsenic element, they will share their electrons, and as a result, each outermost valence shell will now be complete. Hence, we get the compound gallium arsenide. So this brings us to the end of our lecture. Inshallah, next time we will start. So please, everybody, all the class, all my students, please read from the textbook, and inshallah, next time we will discuss a new article. Thank you very much. Assalamu alaikum.